Hello and welcome to Calc Chats 9. Today we're going to be learning about geometric, harmonic, and p-series, as well as partial sums. So first we need to refresh our brains. What is a sequence? So a sequence can be a list or a pattern of numbers. So a sequence could look like 1, 8, 13, and 18. That is a sequence. That is just a random pattern of numbers. And a series is the sum of the sequence. So if we were trying to find the series of the sequence above, we would say, okay, the sum is 1 plus 8 plus 13 plus 18. And we would use this to help us find the sum of the sequence. And so this would end up summing up to 40. So again, a sequence is a list of numbers, series is the sum of that sequence. So we're going to be talking about a couple special sequence or series today. So this is called our geometric series. So we notice that giant kind of S-shaped looking thing, that's the notation for sum. So here we're taking the sum of a times r to the n minus 1. So a is any given coefficient. This could be 5, -2, whatever we want it to be. And then r, we call that the ratio. And it's important to notice that the r, the ratio, is being taken to the n minus 1 power. So our ratio is always taken to a power, the n minus 1 power. So this is asking us to list the first 3 terms of the series, sum from n equals 1 to infinity of 6 times 1/3 n minus 1. And so I'm just kind of going to label these here. We don't really need to, but that 6, that's our a, that's our coefficient, and then that 1/3, that's our r, that's our ratio. And so when we list out the first 3 terms, we're looking at n equals 1, n equals 2, and n equals 3. So all we're going to do is we're going to plug those in to our original series wherever we see n. So n equals 1. I'm going to take 6 times 1/3 to the 1 minus 1. That's my n equals 1 term. My n equals 2 term, that is 6 times 1/3 to the 2 minus 1. And then for the third term, 6 times 1/3 to the 3 minus 1. And then I'm just going to simplify these a little bit. So here I get, this should be 6, this should be 2, and this should be 2/3. So this is the first 3 terms of my given series. So now what we're going to be getting into is something maybe unfamiliar, and this is called a harmonic series. So the harmonic series looks like 1 over n. That's just a very general harmonic series. And it's important to note that n to the 1 is in the denominator. And so that's what makes this a harmonic series when I have just n to the first power in the denominator. So looking at this, it is asking me to find the first 4 terms of the series, n equals 1 to infinity. This should be a 3 over n. And so again, all I'm going to do is when I'm looking at the first 4 terms, I'm looking at n equals 1, 2, 3, 4. And so I'm going to plug those in. So I'm going to take 3 over 1, 3 over 2, 3 over 3, and then 3 over 4. And so we can simplify this to 3 halves, 1, and 3/4. And so that's our first 4 terms of our given series. So now what we're going to start dealing with is called a p-series. And so this is 1 over n to the p. So the harmonic series was 1 over n, but for our p-series, that p is any given power. So we call it a p-series. It's a kind of a power series, but again, that n is in the denominator. That's the important part. So I'm just kind of going to show you some examples. We're not going to list out any terms because we should feel comfortable with that by now. But the sum of terms from n equals 1 to infinity of 7 over n to the 6th. This is a p-series because that 6 is going to be my p. So I'm taking n to the power, and that n is in the denominator. This second one might not look like a p-series, but it is. I'm going to go ahead and rewrite this as 2 over n to the 1/2. So when we're dealing with power series, we can have whole numbers, yes. for our p's, but we can also have fractions. And so that n to the 1/2, that still counts as a power series. So both of these are, sorry, a p series. So both of these are p series. Now we're going to get into what's called convergence and divergence. So you've kind of discussed this a little bit in Algebra 2. We're going to go more in depth with series. And so if a series converge, it gets really, really close to a number or a limit, and it cannot go over that number. We can kind of think of it like an asymptote. So when we take the sums of series, if it approaches a limit, if it approaches that number, we say the series converges. Conversely, if a series diverges, it just increases or decreases without bound. And so what that means is there's no stopping point. There's no kind of end where the series is going to sum to. So every time we add on terms, it's not getting any closer to a number. Even if it may look like it, there are some series that look like they're going to converge, but they actually diverge because our sum keeps getting bigger and bigger. We're going to talk about when geometric and p-series converge and when do they diverge. So these series have certain convergence and divergence criteria for us to meet that we can easily tell any given series. If that series is a geometric or a p-series, we can tell if it's going to converge or diverge. So for geometric, it converges if the absolute value of r is less than 1. So this could look like the sum n equals 1. This could look like the series that we talked about in the slides before, 6 times 1/3 to the n minus 1. My r is 1/3. The absolute value of 1/3 is less than 1, so that series is going to diverge. And if I think about the terms that we listed out, the terms kept getting smaller. It looks like it was kind of getting close to some number. A divergent series, if the absolute value of r is greater than 1. So a divergent series could look like n equals 1 to infinity. This could be 1/3 times 6 to the n minus 1. So in this case, my r is 6. It's greater than 1. So that series is going to diverge. My terms are just going to keep getting bigger and bigger. And as I sum them up, I'm never going to reach a number. So that's for geometric. Now for p-series, our conditions are kind of flip-flopped. So for a p-series to converge, my p needs to be greater than 1. So what this means is we kind of looked at the series n equals 1 to infinity of 7 over n to the 6th. That p attached to that n, what that n is being raised to, that p is greater than 1. So this series is going to converge. It's going to hit a number. Versus divergence, if p is less than or equal to 1. So if we had 2 over square root of n, we could rewrite that as 2 over n to the 1/2. That p, that's a fraction. That's less than 1. So this series is going to diverge. I write p is less than or equal to 1, but when p is equal to 1, remember we have that harmonic series. So we have n equals 1 to infinity of 1 over n. So our harmonic series always diverges. So harmonic always diverges. And this is one that we're going to come across. It looks like it's going to converge. We want it to converge. The terms are getting smaller. If we graph it, it looks like it's going to converge, but it doesn't. So the harmonic series always diverges. And we can use that fact to help us find a lot of other series that diverge as well. So using partial sums. So when we do partial sums, we're basically taking not the whole sum, but the sum of a series up to some number. So if I was given, let's say the series n equals 1 to infinity of, let's say 2 times 7 over n squared. I might ask you, find the fifth partial sum. So basically what this means is I want you to find the sum of the series all the way up to the fifth term. The fifth partial sum all the way up to the fifth term of 2 times 7 over n squared. And so what we're going to do is we're going to use our calculator for this. We're going to go over this in class, but basically all we need to press is math 0, and that gets us to our sum, and we just plug in whatever we want to sum up to. And so in this case, all I'm doing is I'm plugging this box right here into the calculator, and I get that that's equal to 20.4905. So when we're using partial sums, we're going to be able to use a calculator. It's a bit easier, but all we're doing is we're summing up the terms from 1 to 5 for the fifth partial sum. If it was 8, we'd sum up the terms 1 through 8. And so we're going to be using our calculator for this, but it's a little bit easier using that. So this is the end of Calc Test 9. Thank you guys for watching. Please like and subscribe and come to class with any questions that you may have on geometric, harmonic, or P-series.